But before designing or before solve any problem, we have to understand or we have to know about the assumptions and formulations and considerations of IS codes for column. So first of all, let's check out the clause number 39.3 for axially loaded short columns. After that, we will get back to this page and see this formulation, which is made on the basis of IS code assumptions. Okay. Let's check out IS 456 2000. Clause number 39.3 of IS 456 2000 for short axially loaded members in compression. That means axially loaded short column. Let's check out the assumption. The member shall be designed by considering the assumptions given in 39.1 and the minimum eccentricity. When the minimum eccentricity as per 25.4, that means clause number 25.4, does not exceed 0.05 times the lateral dimension, the members may be designed by the following equation. So before check the following equation, let's check out as per clause number 25.4 what is minimum eccentricity. Look, clause number 25.4 minimum eccentricity. All columns shall be designed for minimum eccentricity equal to the supported length of column by 500 plus lateral dimension by 30, subjected to a minimum of 20 mm. Where biaxial bending is considered, it is sufficient to ensure that eccentricity exceeds the minimum about one axis at a time. So whatever written about minimum eccentricity, that is formulated in our notes. After read out all considerations of IS 456, we will see the formulated format of this written one. Okay, that is L by 500 plus D by 30 greater or equal to 20 mm, whatever written here. So let's check again. Let's continue clause number 39.3. So as per clause number 39.3, the formula is PU is equals to 0.4 FCK into AC plus 0.67 FY into ASC. PU is axial load on the member. FCK is characteristic compressive strength of the concrete. AC is area of concrete. Fy is characteristic strength of the compression reinforcement, and ASC is area of longitudinal reinforcement for columns. Now see here, whatever we read in IS code, that is written here for axially loaded short column with rectangular ties. The short column or lateral ties shall be designed by the following equation. If the minimum eccentricity does not exceed 0.05 times the lateral dimension, that is E suffix min, that means E minimum eccentricity is equals to L by 500 plus D by 30 greater or equal to 20 mm. So E minimum is not greater than 0.05 D. So, as per clause number 25.4, this formulation is written here. After that, Pu is equals to 0.4 FCK into AC plus 0.67 Fy into ASC, which we read out just in IS 456. Pu is factor axial load, AC is area of concrete, ASC is area of longitudinal reinforcement of column, FCK is characteristic strength of the compression longitudinal reinforcement. If the minimum eccentricity is greater than 0.05 D, the section is designed for combined axial load and bending. Okay. Note that minimum eccentricity as per code is equals to 20 mm. Therefore, 0.05 D is greater or equal to 20 mm. So, D is greater or equal to 20 by 0.05 or 400 mm, and here D is lateral dimension, as you know. Also, L by 500 plus D by 30 is less or equals to 0.05 D or D by 20. So, L by 500 is less or equal to D by 20 minus D by 30, or we can write 0.016 D. So, D is greater or equal to 0.12 L, where L is length of column. Hence, all column which have D, the lateral dimension, is less than 400 mm or 0.12 L, the minimum eccentricity will be greater than 0.05 D, and hence equation 1 will not applicable in that case. Now check out the design steps. How could we design? Now steps for axially loaded column. So, if factored load Pu is given and material the grade of concrete and steel, first assume suitable percentage of area of steel ASC. It will be vary between 0.8 to 4%. Maximum of the time generally we take 1% for easy calculation. Okay, and ASC is definitely P into AG, where AG is gross area. Now determine AC in terms of AG. So AC means area of concrete, which is definitely in between AG. So AC is equals to AG minus ASC. You can write it. Now calculate AG as follows. So from this equation, which is given in 39.3, Pu is equals to 0.4 FCK within bracket AG minus ASC, that means AC, plus 0.67 Fy into ASC. So we can write it, right? Now putting ASC is equals to P into AG. Now calculate AG as all other terms are known. So number 4, calculate dimension of column as follows. For square column, B square equals to AG. For rectangular column, B into D is equals to AG, where assume B and calculate D. One value we should assume and one we have to calculate. Now provide area of reinforcement and then design as per IS code. Design the lateral ties as per IS specification. Now note that if length of column is given, then we have to calculate effective length on the basis of end condition or support condition, which is given in table number 28. No, where is written 13.1? Not that is wrong. Given in which is given in table number 28 of IS 456 2000. This will be table number 28. Okay. Then check the slenderness ratio and minimum eccentricity as follows. L effective by B should be less than 12. After that, calculate minimum eccentricity as follows. E minimum is equals to L by 500 plus G by 30 is greater or equal to 20 mm, and E minimum by G is less or equal to, it's less than 0.05 for an axially loaded column. Now, we can use design aids like this. The equation which is written and earlier, the equation 1 given above can be rearranged as follows. So, the equation can be rearranged as follows. Pu is equals to 0.4 FCK within bracket Ag minus ASC plus 0.67 Fy ASC, where Ag is gross area of column. Now, putting ASC is equals to P into Ag by 100. So, Pu will be equal to 0.4 FCK within bracket Ag minus Pag by 100 bracket closed plus 0.67 Fy into P into Ag by 100. So, Pu by Ag is equals to 0.4 FCK plus P by 100 within bracket 0.67 Fy minus 0.4 FCK. So, we can rearrange like this. For varying values of Pu, Ag and FCK and P for different value of Fy, design charts have been prepared which are used for design of short axially loaded column. These charts are given in SP16, chart number 24, 25 and 26, which are mainly used for this. Let's solve few problems to better understand the design of RCC column. The first problem is within bracket 0.67 Fy minus 0.4 FCK. So, we can rearrange like this. For varying values of Pu, Ag and FCK and P for different value of Fy, design charts have been prepared which are used for design of short axially loaded column. These charts are given in SP16, chart number 24, 25 and 26, which are mainly used for this. Let's solve few problems to better understand the design of RCC column. The first problem is an RCC short column of size 400 mm by 500 mm is carrying a factored load of 3000 kilonewton. Design the column assuming E minimum is is less than 0.05 d. Use M25 concrete and Fe 415 steel. So let's go to the solution. Small b is 400 mm, that is least lateral dimension. Capital D is equals to 500, that is lateral dimension, and Pu is given 3000 kilonewton, or we can also write 3000 into 10 cube Newton. Now E minimum is less than 0.05 d. Okay. So which satisfied the consideration as per IS code. FCK is 25 Newton per millimeter square for M25 concrete, and Fy is 415 Newton per millimeter square for Fe 415 steel. Now we have to find out area of steel ASC. As E minimum is less than 0.05 d, so factored load is written as Pu is equals to 0.4 FCK AC plus 0.67 Fy ASC. Now AC is equals to Ag minus ASC, right? We have seen it earlier. So here Ag, the gross area, is 400 into 500 minus ASC. So that is equals to, you can see this. So this is the value of AC. So in equation we have to put all the values. 3000 into 10 cube is equals to 0.4 into 25 within bracket, the value of AC plus 0.67 into 415 into ASC. From this equation we can calculate the value of ASC. So value of ASC is equals to 3730.6 mm square. Now we are using 25 mm dia bars. So area of one bar, definitely pi by 4 into 25 square, that is equals to 490 mm square. So number of bars required is equals to ASC by Fi. Total area of steel is 3730.6 by cross sectional area of one bar, that is 490, is equals to 7.6. So we can't use 7.6 number of bars. So definitely we provide 8 number of bars of 25 mm diameter, as you see in figure. Okay. Now time for provide lateral ties. The diameter of tie should not be less than 1/4 of diameter of bar, that is 25. So 1/4 into 25, that is 6.25 mm, and 6 mm. So should not be less than this value, so should not be less than 6.25. So we can use 8 mm dia ties. The pitch of ties should not be less than following: least lateral dimension is equals to 400 mm, 16 into dia of bar, that is 25, which is equals to 400 mm, and 300 mm. So therefore provide 8 mm dia bar at the rate of 300 mm center to center as double ties. The arrangement of reinforcement is shown in figure. Let's check out the figure. Look, there are total 8 number of bars and there are 2 lateral ties given. Okay, so dimensions are given here. 8 number of 25 mm dia bar is provided here, and 8 mm dia lateral ties are given at 300 mm center to center distance. Okay. So this drawing is also important. Here we complete this problem. Let's check out the next problem. Design a short RCC column to carry an axial load of 1600 kilonewton. It is 4 meter long, effectively held in position and restrained against rotation at both ends. Use M20 concrete and Fe 415 steel. Look, in this question, effective length is not given, length is given. Okay, and end condition, that means support condition, is given to find out the coefficient which we have to multiply to calculate effective length. Okay. So length L is 4 meter, P axial load is 1600 kilonewton, FCK is 20 Newton per millimeter square for M20 concrete, Fy is 415 Newton per millimeter square for Fe 415 steel. Now we have to calculate effective length for the end condition, effectively held in position and restrained against rotation. Let's check out table number 28 of IS 456 2000. Look, in table number 28, in extreme left column, support condition or end condition is given. First one is effectively held in position and restrained against rotation in both ends. This is our end condition for this problem. So we have to take the extreme right column recommended values for effective length, that is 0.65 L. So we have to take this value 0.65 L, that means 0.65 at coefficient which have to multiply with the length. So for effectively held in position and restrained against rotation, L effective is equals to 0.65 L, that is equals to 0.65 into 4, that is equals to 2.6 meter or 2600 mm. Factored load Pu is equals to 1.5 P, that is equals to 1.5 into 1600 is equals to 2400 kilonewton. Now assuming 1% steel ASC, so our limit is 0.428%, so we can assume 1%, right, as I told earlier. So that is equals to 0.01 of Ag of gross area, right. So AC is equals to Ag minus ASC is equals to Ag minus 0.01 Ag. So that is equals to 0.99 Ag. So area of concrete is 0.99 Ag. So Pu is equals to, we know the formula, 0.4 FCK AC plus 0.67 Fy ASC. This formula as per clause number 39.3. Okay, now value of Pu is, we have calculated earlier, we just multiply the load factor, that is 1.5 with axial load P. So now our Pu is 2400 into 10 cube, that is equals to 0.4 into 20 into 0.99 Ag plus 0.67 into 415 into 0.01 Ag. So Ag gross area is equals to this value 224299 mm square. So we can provide 500 mm by 500 mm column right. So we have provided this depending upon the gross area. Now slenderness ratio. Slenderness ratio is L effective by B. So L effective is 2600 by B is 500, which we have provided, that is equals to 5.2, which is less than 12. Hence it is short column, right, as it is less than 12. Slenderness ratio, the value of slenderness ratio is less than 12. Now the next step is minimum eccentricity. For minimum eccentricity, we know that is equals to L by 500 plus D by 30, that is equals to 4000 by 500 plus 500 by 30, that is equals to 24.67. So E minimum by D is equals to 24.67 by 500, that is equals to 0.049, which is less than 0.5. So as per this condition is satisfied, hence the column can be designed as axially loaded short column. This is the because this is the consideration of axially loaded short column. Now area of steel AC is 0.01 to AG minus 0.0 sorry, that is equals to, that is not minus, okay, this is not minus, this is printing mistake, this is equals to, this is actually equals to, okay. So AC is 0.01 into AG. We know the value of AG as per design, no, not as per provided area, as per calculated, which is required actually, as per requirement. So AC is equals to 2243 mm square. Now using 20 mm dia bars, the area, cross sectional area of one bar is definitely pi by 4 into 20 square, that is equals to 314 mm square. Now number of bars required is equals to area of steel by cross sectional area of one bar, that is equals to 8. So we will provide 8 numbers of 20 mm dia bars. Okay, that is complete. Now we have to provide lateral ties, right? So for lateral ties, the diameter of lateral ties should not be more than 1/4 of diameter of bar, that is 20, that is equals to 5 mm and 6 mm. So we can use 6 mm links or lateral ties, and pitch of the ties should not exceed the following: least lateral dimension, that is 500, 16 into dia of bar, that is 20, is equals to 320 mm and 300 mm. Okay, so now provide 6 mm dia bar, actually 6 mm dia links or lateral ties at the rate of 300 mm center to center as shown in figure. You can see this figure. In figure, 8 number of bars, 20 mm dia bars is given in this cross sectional figure, and we provided cover 40 mm, and the lateral dimensions are 500 mm each, and 6 mm dia lateral ties are given at 300 mm center to center. Okay. So here the problem, the solution of the problem and the design is complete. That's all for this lecture. Thank you.